The Association of German Engineers and Hypothalamus Artificial Intelligence. Invite to the webinar that will be held on March 26 at 5 p.m. Berlin time. Optimizing Intelligent Operations in Mathematical Port Modeling Project, Port of Cartagena de Indias. Lecturers, Danilo Abril-Hernández, and Jesús María Velásquez-Bermúdez. Hy, through its professionals, and based on its research, has won the following awards. Research in Logistic, 2006, awarded by the Colombian Association of Logistics, Ecolog. Innovation in Logistic Excellence, 2006, awarded by GS1 Colombia and Logica, GS1 Global Network. Part of the results presented have been published in the paper. Optimizing Port Operations to Cope with Shipping Congestion in South American Countries. Published by Informs, Institute for Management Science and Operations Research. The White Paper. Optimization of Logistics Operations in Ports. It contains an overview of this type of project. The White Paper. Modelo de optimización asignación de barcos e instalaciones portuarias. Contains the algebraic formulation. The White Paper. Optimización de operaciones en puertos. It contains an overview of this type of project. And the paper. An integrated event-driven real-time tactical operational optimization framework for smart port operations planning. It presents an academic publication of the work. Hy has developed the Hy Port System to optimize the decisions of companies related to the port sector and the logistics operations that must be faced. Port Operation Modeling Framework. Ports Advanced Analytics. Port decision makers today face the problem of exploring ways to increase port capacity, which is influenced by the continued growth in the number of containers entering and leaving the port, the steady increase in the size of ships, as well as many other factors, previously unforeseen. Therefore, professionals, as well as academics, have become interested in port capacity management and the use of advanced analytics to support their decision-making processes. Applications can be grouped into strategic planning, business planning, operations planning, real-time scheduling of operations, productivity analysis, asset maintenance scheduling. Challenges faced. The port receives multiple weekly services that must be assigned to one terminal. The combinatorics of allocation possibilities is on the order of trillions of possible combinations. Before the project, the assignment was carried out manually, considering the characteristics of the ships, the itineraries of the services and the restrictions of the docks and cranes existing in each terminal. This assignment was made without considering optimality criteria, therefore, there was no guarantee that the established allocation would be optimal. If the terminal planer took a minute to evaluate each alternative, it was estimated that it would take millions of years to ensure an optimal response, obtained from a comprehensive enumeration. Placing a single service in the wrong terminal can easily increase the annual cost of transfers by an order of magnitude of millions of US dollars, since it would be a mistake to be commented on periodically. The table presents a summary of the problems and opportunities in mathematical models of optimization for port operations. Vessel Services Scheduling. Its purpose is to produce the following specific results. The transfer of vessels belonging to maritime transport services, to a dock belonging to a terminal and to a set of cranes that will serve the service, considering the operational restrictions of both the ships and each terminal, their docks and the cranes of each dock. A detailed scheduling, by events, continuous time, of the assignment of ships to the docks. This involves defining the assigned dock, the time of entry, waiting, operation and departure of each vessel. A detailed schedule of container transfers between terminals, considering the previous arrival time of the vessels. The model is operational, it is executed daily or every time an event, or a contingency, occurs that merits the reprogramming of the running program. It is based on continuous time modeling using a mixed linear programming, MIP, model. The Gantt presents a detailed schedule, by event, continuous time, of the assignment of vessels to the docks. A port is conceived as consisting of one, or multiple, terminals to serve ships of different types of transport, bulk products, container ships, vehicle carriers, and cruise ships. The main parameters that characterize the operation of a terminal are berthing lines that are characterized by the distance, draft and load they can support. The storage capacity in different types of sites, yards, warehouses, tanks, silos. The type of products that can be stored at each storage site. The image presents a satellite photo of the port of Cartagena Group, which currently has 4 terminals. The work carried out was based on the existing infrastructure in 2015, which had 2 terminals, Sociedad Portuaria Regional Cartagena, SPRC, and Conticar. The docks of the terminals are the places where ships are located to carry out loading and unloading operations. In a terminal there may be 1 or more docks, which may or may not be associated with certain types of services, for example, cruise ships, container ships, etc. The main parameters that characterize a dock are longitude, depth, and structural capacity. A terminal is made up of multiple docks. The image shows a terminal that has 2 docks. Each pier can be made up of several berths or piers, which can be of variable length. Therefore, the dock must be modeled in such a way that the length of the berthing assignment is dynamic. There is an operational restriction on the distance that must separate the ship with neighboring ships, and the start, or end, point of the berthing line. These separations can be seen in the figure. The quay will be modeled using the quay segment concept, which is defined as a range of the quay where the depth and maximum structural capacity can be considered constant. Terminals docks does not necessarily represent a physical or operational division, it is along the docking line, considered continuous, that ships are placed. The berthing line is characterized by its physical conditions, structural capacity and depth, that must be considered for the assignment of a ship to a position on the line. The physical conditions of the berthing line are not constant along its length. For this reason, the dock must be segmented to define ranges where these characteristics are considered equal, determining a dock segment, or a quay. The discretization of the berthing line, for example, every 10 meters, must be defined jointly between the user and the mathematical modeler. The cranes are responsible for the loading and unloading operation between the ship and the dock floor, for products such as containers and vehicles. Normally a port has multiple types of cranes, among which stand out mobile cranes and gantry cranes. The main features of the cranes are crane type, lifting height, seaside reach, average productivity, movements per hour, and maximum availability. Gantry cranes are located on the quays that can serve 1 or more berths. The limits of cranes are the reach, or the crane width, and the crane height, or the aerial draft. The height and reach of the arm is presented in the figure. It should be noted that these characteristics are common to mobile cranes. Assignment of crane to model services and handling of containers. Its purpose is to produce the following specific items: a detailed schedule of the assignment of cranes to services, and container management considering their destinations. The dock cranes are in the coastal or operational area. The transportation area supports vehicle movements, cranes, trucks and/or trains. The containers are stacked in the container yard. For operations, the terminal area can be divided into 4 large parts: ship to shore, waterside horizontal transport, storage, and hinterland connection area. The courtyards and the interior connection are in the area on the land side. The container yards are organized into clusters, composed of multiple cells; stacks, vertically stacked container groups; map of cells, horizontal, ground level organization of stacked containers; cells, in a stack. Each container occupies a cell, which is located at a certain height, in a specific row. Part of the model's functions must be the stacking and unstacking of containers. To do this, the cell map is used, which has detailed information on each container, destination, or service, and merchandise. The model calculates all the movements that must be made with a container until it leaves the container yard in a service. To do this, it must be ensured that the loading time on the ship is within the ship's time window, and that the position of the container on the ship complies with the specifications given by the shipping company. The storage on the ship can be simulated as another storage area, like those available on land. This work can be carried out by the port, with a ship pallet planning system, or by the ship with its own systems. The container transfer operations at the port are: transfer between the coastal area to the container yard, using the ship's cranes and gantry cranes. Transfers in the storage area, using yard cranes, and transfer between the container yard and the vehicles transporting the containers out of the port, using yard cranes. Port operation modeling. Physical entities. A service is one of the many routes or itineraries offered by a shipping line. One or more boats may participate in a service. For the port, the following data of a service is relevant. Service name. Shipping service is one of the many routes, or itineraries, offered by a shipping line. The standard rule is that one or more boats may participate in a service. For the port, the following data of a service is relevant. Type of arrival. Irregular, randomly up every n number of hours. Regular, up to a set time every n number of weeks. Regular services take precedence over irregular ones, and deviation. If the service is regular, the deviation is a probability distribution that indicates the number of hours a service can be advanced or delayed. If the service is irregular, it is a probability distribution that indicates the number of hours between arrivals. Movements. It is a probability distribution that indicates the number of containers, or vehicles, or tons, that are embarked and disembarked per arrival, and minimum productivity required. It is the number of movements per hour that must guarantee the port to the service. The main characteristics of the service are: name of the service, type of arrival, regular or irregular, and type of boat. Ships are the entities that transport cargo. Their main characteristics are: identification of the vessel, cargo type, deadweight tonnage, length, beam, draft, air draft, number of cranes, maximum number of assignable cranes, and non-assignable cranes. Container transfers between terminals. Some containers that are unloaded are containers in transit that have to be reloaded on other ships to other destinations. Agreements exist between shipping lines for a certain number of transit containers to be dropped off by one line at the port and then picked up by another. Therefore, if one of the lines arrives at one terminal, and the other line arrives at another terminal, a transfer will be generated, the cost of which normally must be borne by the port. In addition to ships, many ports must consider barges, which are vessels dedicated to the transport of transshipment products, containers, vehicles, that must be mobilized between the port terminals. Like any other ship that covers a service, barges make use of berthing lines and cranes. Some containers that are unloaded are containers in transit that need to be reloaded onto other ships to other destinations. There are agreements between shipping companies for one line to drop off a certain number of transit containers at the port and then pick them up by another. Therefore, if one of the lines arrives at one terminal, and the other line arrives at another terminal, a transfer will be generated, the cost of which must be borne by the port. The service window defines the time between the expected date of arrival and the expected date of departure requested by the shipping line for attention in the port. The service window is divided into several times: reserve time, docking time, preparation time, operating time, closing time, departure time, early arrival date, late departure date, and time window slack. Some containers that are unloaded are containers in transit that need to be reloaded onto other ships to other destinations. There are agreements between shipping companies for one line to drop off a certain number of transit containers at the port and then pick them up by another. Therefore, if one of the lines arrives at one terminal, and the other line arrives at another terminal, a transfer will be generated, the cost of which must be borne by the port. The process of accepting a new service at the port's terminals begins with the request by the shipping companies, which provide the port with the following information: number of expected moves, frequency of service, weekly or biweekly, Day, expected time of service arrival, or time window. Physical characteristics of the type of vessel that will provide the service. Based on the information provided by the shipping company, and the current assignment of services to terminals and docks to ships, firm commitments, the commercial area, supported by the operations area, analyzes whether it is viable to provide this service in the port facilities. To do this, it must be to that. The accept a new service, it is important that the port can negotiate minor changes in the service window with the services already in place. Although within the negotiations there is a permitted slack, +/X hours, in the service window, this should not be included in the process of assigning services to terminals and from ships to docks. There are some services that have pre-scheduled appointments, for example the passage through the Panama Canal, so the slack in the departure time must be 0. The hourly fine for non-compliance with the time out of the time window has an average cost in US dollars. The fine depends on many factors and it is not possible to settle it in the same way for all shipping companies. In many cases it is contractually fixed. The vessel's service operation begins in the moment the ship arrives at the buoy point. The duration of these activities is measured in hours. From this point on, the ship is steered by a practical pilot from the harbor pilotage company under the approval of the ship's captain. This first operation ends when the ship arrives at the geographical point where the docking maneuver begins. Next, comes the docking operation that consists of the location or parking of the ship in the section of the dock that has been assigned to it for the unloading operation. The next sub-process is service preparation, which consists of reviewing the documentation and its initial inspection. After the preparation comes the loading and unloading activity, which is the operation itself. In this activity, the ship has the necessary number of cranes, for the necessary time, to comply with the minimum productivity of movements committed to the shipping company that allows the ship to set sail respecting the time window stipulated in the commercial negotiation. During the time of operation, all the activities necessary for the movement of containers to and from the port storage yards are carried out. Next comes the closing activity, which in spirit and time is similar to the preparation activity. Finally, and after the loosing activity, the boat can set sail. For all activities, except for the operating activity, there are estimates of the expected times with very low variability and therefore they are taken as constants according to the suggestion made by the port. The calculation of the operating time is complex as it depends on the resources and/or cranes assigned to the vessel, as well as the duration of their assignment. The problem is formulated using an event-based approach. An event is any situation or milestone that changes the current state of the system. In this formulation we have two ship events: when a ship arrives at port, and when a ship leaves port to continue its journey. The port's business process may be represented by the events referenced: first, arrival at the port; secondly, arrival at the berth; third, end of berthing operations, exit from berth; fourth, departure from the port. The operational timeline can be viewed in more detail. The image shows the period of operations at the berth. The image shows the variables in the model and how they relate. Equations in more detail, ready for implementation. Mathematical modeling. How we build our model up. The table presents the entities used in the model that is described. These are vessel, event, crane, key, dock segment, service, type of service, terminal. Indices represent the entity and all algebraic elements of the model. Below are some groups of equations in the model. These equations describe events that occur over time. A set, occurrence events timeline. This inequality ensures that all events have a different instant of occurrence on the timeline. The epsilon value ensures to avoid degenerate solutions, which slow down the speed of the model. OSER, assignment event. The event can only be assigned to one of the event types that can change the state of the system. Entry or exit of a ship, value of 1, or no change in the state of the system, value of 0. As model preprocessing, the model must calculate the events that can occur in a run. In this way, there is an exact adjustment of the events, and impossible events are not generated. The process to follow is: first, order all vessels based on expected arrival, FEBS, and departure time, FSBS. Second, add 1 to the number of cranes to include the vessel-related entry and exit event. Third, calculate the cumulative number of events up to the nth event, inclusive. Fourth, the events assigned to the vessel are those between the cumulative events of FEBS and FSBS. These equations describe the vessel events allocation. AB, B input assignment vessel to events. It ensures that the entry event of vessel B is assigned only once, considering the possible alternatives of the tuple, dock segment, and event. ABIS, B output assignment vessel to events. It ensures that the exit event of vessel B is assigned only once, considering the possible alternatives of the tuple, dock segment, and event. SEB, TE, M, SM, B, E state vessel segment dock event. This equation allows the coordination of the state of the ship dock berth segment assignment between two consecutive. These equations describe the allocation vessel to segment dock. ASBM, the allocation vessel to segment dock. It ensures that vessel B is assigned only once to a berthing segment SM of the docks where the vessel can dock. PST, TE, M, SM, B input time coordination segment dock and vessel. It ensures that the variable TBEM, SM, B can take a positive value if and only if the vessel B has been assigned to the dock segment SM, of dock M, which occurs when ABM, M, SM, B equals 1. CBSTS, TE, M, SM, B output time coordination segment dock to vessel. It guarantees that the variable TSB, M, SM, B can take a positive value if and only if the vessel B has been assigned to the segment dock SM, which occurs when ABM, M, SM, B equals 1. End operation. We use the same idea to define the TSB, M, SM, B variable for each vessel. The two equations guarantee the synchronization of the event E with the tuple, dock segment, and event, for the variables TIV, E and TSB, M, SM, B. El buque B solo podrá utilizar uno de los segmentos de uno de los muelles. In BC arrive time of vessel B. The initial hour of the operation of load or unloading of the vessel B in the segment dock SM, variable TEB, M, SM, B, must be greater than or equal to the arrive time of the vessel, parameter IAD, B. That is equal to FEBS, B, ship arrival time, less slack of the window service, parameter HOLG, B. I4B instant completion operation in vessel B. It guarantees that the moment of completion of the operation of load or unloading of vessel B is greater than or equal to the moment of completion of the operations of load unloading of each one of the cranes that serve the vessel. The diagram presents the coordination equations related to the events that happen to a vessel. I4B instant completion operation in vessel B. It guarantees that the moment of completion of the operation of load or unloading of vessel B is greater than or equal to the moment of completion of the operations of load unloading of each one of the cranes that serve the vessel. FSBC, the instant completion of service vessel containers. It determines the moment of completion of the service for vessels carrying containers. These equations control the running time of a crane between events. CTBG, TE, M, G, B, E coordination operation time crane vessel event. It allows the variable TGB, M, G, B, E, operating time, take values greater than 0 only when crane G is in operation the vessel B in the event E. The same concept used to define the TEB, M, SM, B and TSB, M, SM, B is used here to determine TGB, M, G, B, E for each crane vessel combination. To solve the model, in 2016, it was decided to divide the problem to solve it in parts. This was agreed with the end customer. The first model is the terminal service assignment model and solves the problem of assigning ships to terminals. It includes the estimation of the costs of transshipments. The second model, the terminal activity scheduling model, is executed independently for each terminal, considering as a boundary condition the assignments made in the first model. These models, which are the most time-consuming to solve, can be run in parallel. Hy and SPRC recognize that this approach provides a suboptimal solution in close proximity to the optimal solution. The experiments carried out showed that the optimality gap in many cases was zero. Within the squares, the variables as they were divided in the two models are indicated. Large-scale mathematical modeling. Bender's theory. Sliding optimization. The idea of sliding optimization is that, although an integrated system implies that all its variables are related, and that therefore their optimization must be joint, to the extent that two variables are distant in spacetime this relationship tends to fade, and it can be thought that at the two extremes the influence disappears. Sliding optimization divides spacetime into sub-problems that are solved sequentially, starting with the first and covering the space bounded by the B ships. The time is determined by the departure cutoff time of the last ship of the problem. Then the next problem is added, which overlaps the last ships of the first problem, and introduces additional B ships. This is to ensure a smooth chain of sequential issues. When the problems that cover all the ships have been solved, all the problems together completely cover spacetime. Slide optimization allows to move from an integrated approach to a decoupled and coordinated approach. In the case of ports, Hyport works based on three stages as presented in the following diagram. The steps to follow are described below. To carry out the programming of a terminal, the first N services are taken according to the expected date time of arrival at the port. With this subset of services, Hyport gets a schedule that minimizes the departure time of the last ship within the N scheduled ships, which guarantees that for the following SKN services the greatest amount of time is available for its programming, which facilitates the feasibility of the problem. The value of N is determined empirically based on knowledge of the behavior of the system. Setting as a border condition the programming of the first NM services to be attended, the programming of the following NM is carried out, including the last M services that were already pre-programmed. The value of M is determined empirically based on knowledge of the behavior of the system, it must be less than N. The process ends when all the SK services of the terminal have been scheduled and stage 2 ends. As a result of stage 2, a feasible initial solution to the programming problem has been created, close to the optimal solution of the problem, and this allows the algorithm to move to stage 3. In stage 3, Hyport proceeds to run the optimization integrated for all the services that have been assigned to each terminal. The feasible solution built in stage 2 is provided as an initial solution to the problem that is solved in stage 3, which is not identical to the model used for the creation of the initial solution, due to the following differences. The first consists of a set of additional constraints that measure the deviation of the windows of the services that close the planning cycle, and the second is the objective function that is to minimize the cost of the operation, which includes minimizing the payment of penalties for noncompliance in the service window, and a penalty of deviations from the service attention windows of the services that close the planning cycle. As a result of stage 2, a feasible initial solution to the programming problem has been created, close to the optimal solution of the problem, and this allows the algorithm to move to stage 3. In stage 3, Hyport proceeds to run the optimization integrated for all the services that have been assigned to each terminal. The feasible solution built in stage 2 is provided as an initial solution to the problem that is solved in stage 3, which is not identical to the model used for the creation of the initial solution. Inputs. All mathematical models share a single data model, making it easy to interconnect models along the decision-making chain. Below are some shell windows containing the tables of the Hyport information system. The screenshot presents an Optex explorer of the elements of the Hyport information system. The shell window contains the master table of terminals, and the tables of relationships between the terminals and ships and keys. The shell window contains the master table of keys, and the tables of relationships between the keys and terminals, cranes, and ships. The shell window contains the master table of cranes, and the tables of relationships between the cranes and keys. The shell window contains the master table of ships. The shell window contains the master table of ships, and the tables of relationships between the ships and terminals and keys. Outputs. Below are some shell windows containing the results tables of the models of Hyport. The screenshot displays an Optex explorer of windows for the output of a model. The selected table points to the variable time of entry of the ship to the dock. The image presents a selection of a pivot table in Excel with the schedule of services per key. The image presents a pivot table with the crane utilization time per service. The image presents a pivot table with the crane utilization time per service. This is a Gantt chart of keys, cranes, and ships. This is a Gantt chart of key SO5 and ships. This is a Gantt chart of key SO6 and ships. This is a Gantt chart of key SO7, SO8 and ships. This is a Gantt chart of keys and cranes. Thank you for your attention.